Hi everybody and welcome to a new exciting video in the Generative Music AI course. In the previous video we took a look at the ethical implications of generative music. Today we're going to start getting into the technical aspects of generative music. In particular, we're going to look at symbolic and audio representation as well as generation. Let me show you the different topics that we'll be covering. There's a lot of things to cover here, so let's get into it. First, we're going to take a look at what music representation is and why it is extremely important for generative music. Then we're going to dive into the symbolic world. In particular, we're going to look at different types of symbolic representations, how we can use symbolic representation to generate music, and then we're going to take a look at the advantages and disadvantages of symbolic representation. Then we're going to move on to the other side of the moon, that is audio representation. We're going to take a look at audio generation, and we'll finish off by looking at the pros and cons of audio generation. I want to start this lecture by asking an interesting question, a fascinating question. Where does music live? It may sound like a very weird question, but it is not. So, one level where music lives, especially for composers in the Western musical tradition, is in a score. This is the level where music theorists, musicologists, composers talk about music. And this is a level where we notate, or a composer notates, all the necessary information that he or she should pass over to a performer to perform that music. Now, let's assume that the composer indeed passes the score to the performer. What does a performer do? Well, he or she will perform the music and transform something that's on paper in an air pressure wave. So music will move from a notation, a symbolic representation, towards an audio, a sound-based representation. At the end of the day, we're talking just about a simple air pressure wave. This is the level where we have physicists, sound designers, and audio engineers, sound engineers that can study the phenomenon. For them, music equates to this level. It's just sound. But the musical journey doesn't end here. There's another level, because in a performance, we don't only have a performer, but we also have a listener, an audience, a receiver. And so the perception of music is an important part of music, and indeed we could think of it as a sort of like third level of abstraction, third level of representation. And indeed, if you listen to music, you are going to get a mechanical signal that's just like this air pressure wave that's going to hit your ears, and then that signal is going to be transformed into brain activity. And this is another level of music representation, and that's the level of cognition and perception. And indeed, this is the field of study of people who work in music cognition or neuroscience. Now, this may sound a little bit weird that we have this weird representation of music in the brain, but it is indeed a representation, and there's been a fantastic paper that has come out the last summer in 2023, I think it was August, and it was something that blew completely my mind. So these researchers were able to train a model to use brain waves to reconstruct a piece of music, and that piece of music was the famous piece by Pink Floyd called Another Brick in the Wall. So let's listen to this because it's quite amazing. Of course, the reconstruction is by no means perfect, but you can definitely hear that chorus there. And it goes like this. All in all, it's just another brick in the wall. Yeah, sorry for singing that because I'm terrible at that. So let's listen to this. It's quite amazing. It's just a brick in the wall. Okay, yeah, so that's it. Quite amazing, isn't it? Now, all of this just to say that there are so many different levels we can represent music, we can encode music, but all of these levels we've analyzed so far, so a score, sound, and this brain activity can't It's not a perfect representation for our generative music models. So what do we want to achieve with music representation for our generative models? Well, at the end of the day, all we need to do is to encode music in a format that can easily be fed into an algorithm. This is easier said than done. So let me give you like this visual representation of what I just said. So we need to encode music in a way here that makes sense, that works when we want to feed it into a generative music system. It could be a neural network, it could be a generative grammar, it could be a Markov chain, it could be whatever, but we need to find a good representation. And why do we need to have that good representation of music? Because, and this probably is going to surprise you, a good music representation solves more than half of the generative music problem. If you have a strong music representation, you can pack a lot of information in there, and then the model is going to be able to reason, to manipulate, to learn, extract patterns from that representation. If I had a magic wand, what I would like to see in a music representation are these 4 different characteristics. First of all, an ideal music representation should be objective and quantifiable, so that I can always rely on that, and because it's always consistent. Then it should be easy to manipulate, so I should have tokens that I can easily, or algorithms should be able to easily edit and manipulate. It is extremely important for such a representation to capture all the musical details. What do I mean by musical details? Well, it's all the different musical factors, like for example, harmony or melody, structure, rhythm, or performance and production nuances. I want to encode all of that information efficiently, and that's the 4th point. For a music representation to be ideal, it should be very compact. And that's very important, because if I have a compact representation, then it means that I'm going to be able to train models that don't need a lot of parameters, because the whole representation of music is quite compact. The data is low dimensional. In generative music, so far, we've identified a couple of strands of music representations. So one is symbolic, and the other one is audio-based. I guess you can guess where we're going with this argument, but I don't want to anticipate anything at this point. But what I want to say is that there's quite a lot of tension between these two, not about these two representations, but also about the proponents. And indeed, you usually love one or the other. In my case, I really love symbolic, even though lately I've experimented with audio-based generation models quite a lot, because they're super trendy right now. Let's dive into symbolic first. What is a symbolic representation? Well, the name gives it away completely, doesn't it? We use symbols, tokens, to represent music. You can have tokens that represent notes, instruments, all sorts of information about music. And this is like very similar to a score, because if you think about a score, what you have is symbols on a sheet of paper, and that's it. And so basically we can have a digitalized form of that, having symbols, having tokens that we can easily manipulate. Now, there are a bunch of different types of symbolic representations out there. I'm going to list a few of them, but be sure that you're going to be able to find way more than this. And most of the time people tend to create also their own symbolic representations of music, depending on the type of task that they are currently carrying out. So let's get started with the most famous one, perhaps, MIDI. That's a protocol that musical software, musical hardware leverage in order to transfer musical information. So for example, if you have a DAW, like for example Cubase, and you have a keyboard, and you want for those two to communicate musical information, you're going to be using the MIDI protocol. Now, with the MIDI protocol, we can sort of like formalize a note event, a musical event. It's a simple tuple where you have 3 pieces of information. You have a timestamp, So when that musical event starts, then you have a MIDI note, and then you have a velocity. So the MIDI notes is basically the pitch, and it varies from 0 all the way up to 127. Same thing for the velocity. Velocity being a proxy for musical dynamics. So low velocity is basically sort of like piano dynamics, whereas like a high velocity number is a forte or fortissimo dynamics. Now let's move on to another type of representation that's also like quite used, and that's called music XML. So what is that? Well, it's just like a simple structured file, XML file, but it has a twist on top of it. That is like that this XML is tailored in such a way that it can be used to represent music very effectively. And so here you see like this XML, typical XML structure that represents this piece of music here, this piece of notation here. And as you can see, you have different tags like pitch, and inside pitch you have like different information like the step, the alter here, the octave, for example, and the duration and the type. And all of this is a note tag that embeds all of that other information. And as you can see here, you have a lot of information about the compositional aspects, and you can easily manipulate them because these are tokens that you can use. Let's move on. Another type of symbolic representation that's overwhelmingly used is so-called piano roll. And if you've done any music production in any digital audio workstation, you will be familiar with this representation because it's just like the typical grid that you have in your DAW, where a note is just like an event in this grid, and you have basically two axes. On the x-axis you have time, and on the y-axis you have pitch, different notes that you can actually trigger there. To encode a music event with a piano roll representation, we can use a simple tuple with 3 pieces of information: pitch, time when the event starts, and the time when the event ends. Next, we have another type of symbolic representation that's very typical for guitar and bass. That's called a tablature. Rather than having the typical staff notation here, we have all the different chords represented here, and then these numbers represent the number of frets that you want to trigger on your guitar, for example. How do we encode this mathematically? Well, once again, we have a tuple with 3 pieces of information: the string number, the fret number, and the duration of that particular note. There are also fancier ways of representing music as symbols. One of these representations is called the ABC notation, and it's a text-based representation. Here you can see the representation in ABC notation of Twinkle Twinkle Little Star, specifically the first 4 bars. So here you have the title, Twinkle Twinkle Little Star, you have the time signature, that's 4/4, you have the key, that's in C major, and here you have all the necessary information, the actual notation, so C, C, G, G, right, and each of these is going to be a quarter note, and here with this vertical line is going to be dividing 2 bars. And here in the second bar, you'll see that we have this G2, 2 being a half note. So you get the idea. This is a very handy representation that you can use for feeding musical information into a generative music system, like for example, a neural network. Can is another type of notation, symbolic notation of music that descends from ABC notation. And indeed, you can see some similarities here. First of all, you have information about the time signature, that's 4/4, key, here it's empty in the brackets here, which basically means it's the default one, that's C major. And then here you have information about the different bars. And once again, we are notating Twinkle Twinkle Little Star. The 4 initial bars of it, and you have like 4C, and the 4 represents the duration, so it's basically a quarter note, and that's a C. And then you move on and you can read all of it like quite easily. And once again, this is a textual representation of music. And as I mentioned, there are way more symbolic representations than this. Very often researchers use their own representation, symbolic representation of music. In my career, I've created a lot of different symbolic representations. And it is important to know and understand that depending on the type of task that you're trying to carry out, you're going to need a different type of symbolic representation if you decide to go symbolic. Let's take a look at the disciplines that are somehow connected to symbolic representations of music. Well, I would say like that music theory is especially connected to symbolic, because at the end of the day, you're always going to be dealing with scores one way or another. Same thing for composition and computational musicology. And probably I would say that this is one of the reasons why I really love symbolic representation, dealing with symbolic models so much, because you can leverage your own understanding of music and music theory in order to craft representations that are as musically meaningful as possible. How does symbolic generation work? Well, it's quite straightforward from this very high level perspective, but in a nutshell, what you do is you feed a lot of music represented symbolically to a generative music system. You can train it, or it could be a rule-based system. It doesn't really matter. But then you get an output that's also symbolic. Obviously, there's a lot of complexity hidden inside this generative music system black box, because it can be extremely complex, but this is the gist of it. MuseNet is an amazing example of a generative music system that leverages symbolic representation. It was published by OpenAI in 2019. It used a transformer architecture, in particular GPT-2. They used some unsupervised learning to train this generative music model using a lot of MIDI files. A lot. And when I say a lot, I mean hundreds of thousands of them. Okay, and what it does in the end, it basically just like predicts the next token in a sequence. So you can feed an initial sequence of notes, and MuseNet is going to give you the next token, the next note. Let's listen to some examples created with MuseNet. So here you have the whole MuseNet website, and now down here you have different things. Like for example, this one. So you have a prompt, the initial notes are 5 notes of a Frédéric Chopin musical piece. Let's listen to it. Okay, now let's listen to another prompt. So this is jazz, piano, bass, drums. Interesting, isn't it? Symbolic generation comes with a lot of advantages, but also with a lot of disadvantages. Let's take a look at the pros first. We can say that symbolic representation is extremely compact. You can pack a lot of compositional information in it, and the size of these sequences is very, very small. Symbolic representation is very easy to manipulate, because at the end of the day, you're dealing with symbols, tokens that you can edit however you want. It is very clear and precise, because you know all the different instruments in a score and all the different pitches which come from different instruments, and you can pinpoint them. You have a lot of compositional info here, because of course you can extract that info directly from this representation, like for example key, time signature, phrase, sections, and stuff like that. If you train a deep learning model with symbolic representation, a big advantage is that it is able to capture long-term dependencies. And that's the case because the representation is very compact, so the sequences are not really long, and it's way easier for an architecture like a recurrent neural network or a transformer to pick up on the long-term dependencies. And also another advantage of these models is that they tend to be quite small in terms of parameters, and it's easier to train them because you need way less computation. And once again, this goes back to the fact that this representation usually tends to be very compact. Unfortunately, symbolic representation comes also with a lot of disadvantages. First of all, it is a very simplified version of music that doesn't capture all the different aspects of it. And this is also a shortcoming of traditional scores. And that's the beauty of music in a sense, because there's a difference between the score, that's a sort of initial script, and then the performance of it. And you have a lot of different interpretations, and that's what makes interpreters great, the way they interpret the score. But this can be a problem when you want an algorithm to generate music, but you have oversimplified musical representation. And there are certainly some musical limitations, like for example, how can you capture all the nuances of a synthesizer sound with symbolic representation? It's just impossible to do it. And that's because symbolic representation can only have limited details about performance and production. You can't really have a lot of information about, say, reverb or type of distortion and how it sounds. And also another problem, but that's related with models, not just representation, but symbolic models, is that they don't output audio, they just output symbols. So you have to go the extra mile to get like that score basically, and then render it to audio somehow. Symbolic generation is ideal whenever you're dealing with a type of music where there's a lot of structure and the focus is on the compositional side of it, on the pitch, duration, musical structure. And that happens very often with notated Western music, like classical music, orchestral music, music for video games, the orchestral one, or piano music, or even jazz music. But symbolic music really doesn't work well whenever the main focus is not on the composition, but rather on the production. Like for example, what we have in electronic dance music or in drone music, where the beauty of the music is not in the notes themselves, but rather in the sound design part of it. And of course, you can't really encode that information through symbols, or you can try to do it, but it's not really efficient. We are halfway through this lecture, but before we move on, I just want to remind you about the Sound of AI Slack community. There we have discussions about all the topics that we cover here in the Generative Music AI course. So if you haven't joined up yet, I'll leave you the link to join up below in the description box. Okay, we'll now take a look at the other side of the moon, that is audio representation. This is quite straightforward what it is, right? Audio representation is basically the content of the wave files that you listen to. That's an audio representation of music. There are different types of audio representations. The most important one, perhaps, is the waveform itself, but we have others. Like for example, transforms of a waveform, like a spectrogram. So you can take a waveform that represents music or sound more in general in a time domain, you can apply a transformation and get a spectrogram. That transformation is called a Fourier transform, and you're going to get a spectrogram that basically has information about that initial sound in two axes. So the x-axis is going to be time, the y-axis is going to be frequency, and as you can see here you have a representation of a spectrogram, and it's basically a heat map, because at every point in this grid for a particular time and frequency band you have a color that represents how present that frequency band is in that particular point of time. The brighter the color, the more present, the stronger that frequency band is. Spectrograms and other types of transformations are complex topics, but I do have a full course called Audio Signal Processing for Machine Learning that you can check out if you want to dive deeper into this kind of concepts. Just for spectrograms, I'm going to link you a video where you can learn a lot about it. Beyond spectrograms, we also have other types of audio representations, and we can call them audio embeddings. And what are these? Well, this picture here represents it on a very abstract level. So you start with a waveform, and then you have a model that's a bottleneck like this. So this is a machine learning model usually. So you pass the waveform through this bottleneck and you get a more compact representation of that particular waveform. This is called an embedding. And the advantage of this is that you're going to get a representation of that piece of music or that sound, because you can apply it also for speech, that is more compact. And as we've seen, there's a lot of advantage that comes with dealing with more compact representations of music when we deal with generation. There are several disciplines out there that are strictly connected to the audio representation of music. Digital signal processing is a clear case in point here. You need to have knowledge about audio DSP to deal with audio representation of music. Connected to DSP, you have music information retrieval. Of course, you can have symbolic tasks in MIR, but the overwhelming majority, at least today, lives within the audio representation of music. Then, of course, you use audio representation for sound design and also for music cognition if you really want to study how music affects the brain. There are different types of audio-based generations. We can use an end-to-end waveform approach where we feed a waveform directly into the generative music system and we get out another waveform. A problem that we have with this is that waveform representation of music is very highly dimensional, so the size of these models and the look back capacity of these models is problematic. Another approach is to use transformations of a waveform. So for example, you can start with a waveform, you transform that waveform into a spectrogram, you feed that spectrogram into a generative music system, and you get out as a generative output another spectrogram. And at this point, you could use an inverse Fourier transform for moving from a spectrogram onto a waveform. There are also more complex architectures for generating music leveraging audio, like for example using embeddings. So what you can do is you just feed in an initial waveform and then the model itself extracts the audio embeddings and then it generates new audio embeddings, and then those audio embeddings will be decoded into a waveform. And this is the kind of approach that we'll see when we'll study a music gen later on in part 2 of the course. Talking about audio-based generative models, I just want to mention a few that are extremely important in the literature, and we've seen all of them already in a previous video, so I'm not going to get into them once again in a very detailed manner, but let me just mention them. So we have Jukebox from OpenAI, MusicLM from Google, MusicGen from Meta, and Grave, developed by an academic institution called IRCAM. Obviously, audio generation also comes with its advantages and disadvantages. Let's take a look at the pros first. The most important advantage of an audio representation is that it captures all the performance and production nuances and information, and that's because this representation is very complex and rich. Another great point of an audio-based generative music system is that it outputs directly an audio file without the need of doing an audio rendering somehow from a score. Now let's take a look at the disadvantages. I already mentioned this somehow. The problem of an audio representation is that usually it tends to have a large dimensionality, and the size is very, very big. And that is a problem because it basically adds a lot in terms of computational complexity, number of parameters, and the amount of GPU that you have to throw at these models. Also, another issue is that this type of representation is difficult to manipulate because the representation is not clear and precise, because you really don't have symbols, you don't have entities that you can map onto things that make sense from a compositional standpoint. Also, if we move on to audio-based generative music systems, we know that usually their model size tend to be quite large, and the reason is because of the large dimensionality of audio representation, and at the same time, because of this issue, it is difficult for these models to capture long-term dependencies. And this is why, over time, researchers have experimented with embeddings that could make these representations more compact. Audio-based generation is ideal for all of that type of music where performance and production is king. Like, for example, in EDM or drone music. By now, you've probably understood that symbolic generation and audio generations are a little bit like yin and yang. And the reason is because what symbolic is great at, audio it's not great at, and vice versa. What audio shines at, symbolic doesn't shine at all. These two types of representations of music and generative modalities are somewhat complementary because they bring different things to the generative music table. This lecture was a deep one, wasn't it? But we are at the end of it. So before we conclude, let's just go through the most important points that we made in this lecture. First, a good music representation is an amazing good start for solving generative music. Symbolic representation is similar to a score in that we have symbols and tokens that you can easily manipulate, whereas audio representation uses waveform or transformations of waveforms as a way of encoding music. Symbolic has a lot of compositional details because those constituent tokens can be mapped directly onto musical entities that carry a lot of meaning. By contrast, the audio representation has a ton of performance and production details because it is extremely complex and rich in its representation. Generative music models that use a symbolic representation tend to be smaller because a symbolic representation is more compact. The problem that comes with it is that the output is just a symbolic score that you need to render to audio. Audio-based generative models tend to be very large. You need a lot of GPU in order to train them, but they have an incredible advantage, and that is the output is already audio with all the details about performance and the nuances of production. Woo! We've made it! Congrats! Next time, we're going to look at a very important topic, and that will be a review of the most important generative techniques that we can use to generate music. Before you dash off, please remember to leave a like, and if you're not a Sound of AI subscriber, please subscribe, because it's going to be crazy the amount of good value that you're going to get out of it. That's all for today. I'll see you next time. Take care.